Hello. In this video, we are going to talk about the physical parameters that affect the runway and what corrections we have to take into account if we do not have the design manual of the airport of a certain aircraft. In principle, in the design manuals of a certain aircraft we have some tables, but if we do not have that, we can apply some standard corrections. First, there is the definition of the reference temperature of the airfield, which is the monthly average of the maximum daily temperatures corresponding to the hottest month of the year, this being the one that has the highest monthly average temperature. What does this mean? We take every month of a year, we make the average temperature. The one that has the highest average temperature, we take it and we take all the maximums of all the days. We make the average of those maximums, and that is the average that we have to use. We take this one from several years, just in case a year is especially hot or especially cold, and we have the reference temperature of the aerodrome, which is what we are going to work with. What is this used for? The aircraft, when taking off or landing, needs more or less runway in function of several things. One, for example, is very clear if it has the wind in its face or tail. Another is if the runway is wet, it will take longer to break, or if there is ice. And apart, there are a number of things that influence, let's say, the atmosphere and the configuration of the runway. And for these, some standard corrections are defined. If there is more altitude, we would need more track. Why? Because the air is less dense, less support, and we need more runway. This affects both landing and takeoff. If there is more temperature, the air is also less dense and affects us for landing and takeoff. But studies show that for landing it affects much less due to the configuration of the aircraft. Because in the landing distance a parameter corrector has already been taken into account. And also because one of the things that temperature does is that it affects the reactors. Because to obtain power, a reactor works with the temperature difference between the combustion chamber and the outside. If, of course, the outside temperature is higher, the reactor has less power. And when we are landing, the engines tend to slow down. Really, when we need the power of the reactors, it is in the takeoff. So, the temperature correction is only applied in the takeoff. And then, in tracks of more than 900 meters, the correction is applied by slope, because, obviously, if we have more slope, we will need more track to accelerate. Here we have the data. A 7% for every 300 meters of elevation, both in takeoff and landing. A 1% for every degree that the temperature exceeds the temperature of the ISA atmosphere for that altitude. That is only used in takeoff. The ISA atmosphere has a formula that says that it is 15 degrees at sea level, and it goes down to a ratio of 6.5 degrees for every 1,000 meters to 11,000 meters. So we have here a formula that we can use to calculate the temperature and calculate that difference with the reference temperature of the aerodrome and get the correction. If the effect of these two combined is greater than 35%, we have to do a specific study. And finally, if the track has more than 900 meters, for each 1% of slope, we have to put a 10% of correction in the takeoff. All these corrections we will use later. Well, first we are going to see the formulas. Here you have them in meters, a 7% for every 300 meters, a 1% for every. Here the formula of the ISA atmosphere is not incorporated, and a 10% for every 1% of slope. This has to go in so many percent. If it does not go in so many percent, we will have to multiply this formula by 100. Here we have the formula, and we have the same formula in feet, and already with the formula of the ISA atmosphere. If you want to use this formula with meters instead of 984, it will be 300, and instead of 3,280 it will be 1,000, and that's it.